The squeeze theorem works by squeezing a function between two other functions having known limit, let's say at a point A. It is useful in evaluating the limits of trigonometric functions, and also when we have when we have an unknown function or a function with limit at a point, let's say a point A cannot be evaluated algebraically. So suppose that we have three functions f, g, and function h. And we have a point A on the x-axis and a point L on the y-axis, such that for any x, the values of g will always be between the values of f and h. So we say that g is squeezed between f and h. So you can see this visually, that since the graph of g is between the graph of f and h, then the function values of g would always be between the function values of f and h. So we say that g is sandwiched between f and h. Formally, the squeeze theorem states that if we have three functions f, g, and h defined for all x over an open interval containing a, these functions may not be defined at a. And if the function g is squeezed between the functions f and h, and if we have a real number L such that the limit of f and the limit of h as x approaches a is equal to L, then we say that the limit of g of x as x approaches a must also be equal to L. Here are some trigonometric limit functions which were proved using the Squeeze theorem. For now, we will just use them in evaluating trigonometric limits, and I will show the proof in a different lecture snippet. So we have the limit as theta approaches 0 of sine theta over theta is equal to 1. From here, it implies that the limit of the reciprocal must also be equal to 1. Another form is when we have the limit of 1 minus cosine theta over theta as theta approaches 0 is equal to 0. And this also implies that the limit of cosine theta minus 1 over theta as theta approaches 0 must also be equal to 1. Now let's examine the limit as x approaches 0 of sine of 2x over x. Now observe the numerator is a trigonometric function with an argument that is equal to 2x. When we evaluate this directly, we will get sine of 2 times 0 over 0, which is equal to sine of 0 over 0. And we know that sine of 0 is 0, so we get an indeterminate form. Now we know that when we have indeterminate forms of the form 0 over 0, then we need to manipulate the function in order to reduce the terms that make the numerator and denominator 0. So for this case, we will transform sine of 2x into an entity of the form sine of 2x over 2x in order for us to apply the theorem that was presented earlier. But take note that when we have functions, for us to not modify the definition of the function, we can only multiply to it an entity that is equal to 1. But we have to make sure that we find an equivalent entity that is useful for a function. So for our case, we need a 2x in the denominator. We already have an x. So what we need is 2. So therefore, we will multiply it by 1, which is equal to 2 over 2. So we have this. Okay? Now we will factor out sine of 2x from here. So the numerator, which is 2x, and then we have the denominator x times 2 or 2x. So we're left with a constant multiplier which is equal to 2. So we just rewrite that, and then we will apply the product law. That is, we distribute the limit to the factors. Okay, so we have the limit of a constant, and then we have the limit theorem. Now, as x approaches 0, 2x also approaches 0. So therefore, this is equivalent to the limit of 2 as x approaches 0 times the limit as 2x approaches 0 of sine of 2x over 2x. So in this case, it's like you're saying that theta is equal to 2x. So to continue, we know that the limit of a constant is just a constant. So the limit of 2 as x approaches 0 is 2. And then the limit of sine of 2x over 2x as 2x approaches 0 is just 1. Hence, we have the limit of sine of 2x over x as x approaches 0 is equal to 2. As a recap, we have the Squeeze theorem, which says that if we have three functions f, g, and h, where g is sandwiched between h, and these functions are defined at an open interval containing a, except maybe possibly at a, and suppose that we have a number L such that the limit of f as x approaches a is equal to L, the same with the limit of h as x approaches a is also equal to L, then the limit of g as x approaches a must also be equal to L.